During my presentation, I will follow this agenda. First of all, I will do an introduction. I will describe the HydroQuebec power utility, and also I will focus on the distribution network and gives you more information about the number of assets and show you that it's a complex system. After what, I will try to convince you why is it important today to know the exact location of the power poles and power lines. If you have some concern about the outages or about the reliability of your distribution network, this is a central question. This is an important question. And I will show you how, with the LiDAR data, how is it possible with a point cloud, it's possible to detect and to know the exact location of your overhead power lines and also of your power poles. So I will show you how our algorithm is able to process a huge amount of point cloud from LiDAR data and to extract and step by step to identify the location of poles and step by step to be able to extract the power lines. So I will show you a lot of picture. For that part, after what, I will describe the limitation of our algorithm. And recently we start using a deep learning algorithm and frustum extraction, and some of the deep learning technique help us to overcome limitations of our algorithm. And I will end my presentation with a conclusion and future work. But don't worry, there's no equation on my presentation. There's a lot of picture to help you understand the process of our algorithm step by step. HydroQuebec is a power utility. It's located in Canada in the Quebec province, and we are one of the biggest company in Canada. We have about 20,000 employees, and 90% of our production is from renewable energy. Because of the Quebec geography, we have a wide transmission network because most of our production are located in the north of the Quebec province, and our consumers are located in the south of Quebec province, like Montreal or Quebec City and so on. So that's why we have to travel to transmit the energy from the north deep to the south of the Quebec province. Now, let's focus on the distribution side. We have 4,000 customers, and also we have a complex distribution network because we have more than 120,000 kilometers of overhead power lines, which is really a wide, a large, a huge distribution network that we have to take care of it. So let me give you some information and numbers about our distribution assets or distribution network. We have more than 2.2 million power poles. Most of them are wood poles, as you can see in the picture. Also, we have more than 500,000 power transformers. In addition, it's a small number of underground power transformers. When you have underground lines, you have to use underground power transformer. Actually, we have 50,000, and we have switches and breaker. What is important here is to know that our distribution network is a complex system. We have a lot of equipment, of assets, and we have a wide, huge distribution network that reach 120,000 overhead kilometers of overhead power lines. Now, if you can pay attention to the picture, you're gonna notice that the power pole has a specific shape. It's a cylindrical shape, and also it has a specific color. It can be gray, it can be beige, it can be sometime green, but for sure it's limited to those colors. You can't find blue, let's say blue power poles. And also the direction, the orientation of your poles is always vertical. So for human, it's easy to spot power poles in a picture like this. For HydroQuebec, 90% of our network is aerial. So, and I guess it's this almost the same thing for other power utilities, because building underground network, it costs 10 to 100 more than building in a rural or overhead power lines. So for us it's 90%. And the problem with the overhead power lines is when you have trees or branches that are close to your network, so most of your outages are because of the vegetation. Once you have a branch or a tree that touch the medium voltage of your network, it can cause an outages, and it will reduce the reliability of your distribution network. So for us, 60% of our outages are because of the vegetations. And also, we discovered lately that the global warming is changing our way to deal with the outages. So we are facing more extreme weather conditions. The frequency is higher than before. Let's say it's higher for the last 10 years. And also we discover that even if the duration of those extreme weather conditions is less than before, the frequency of the outages are higher than before. And this causes more outages, vegetation outages. And the main question for the distribution network is, how is it possible today to reduce the outages, vegetation outages? And today we know like two ways to do that. The first way is to replace some of our overhead power lines by an underground cables, which is really expensive, or to do what we call by vegetation control. And by vegetation control, we have forester. They spot like where is the vegetation and where are located the power lines, and they start doing trimming trees, sometime cutting branches, or sometime even worse, they cut the whole tree. So, two ways to reduce outages caused by vegetation: the vegetation control by trimming trees, or replacing your overhead power line by underground cables, which is really expensive. When you start trimming trees that are close to your network, you reduce the outages and you improve the reliability of your distribution network. As simple as that. However, inspecting by a forester all of your distribution network, it's impossible, because you have, like for us, you have 120,000 kilometers, and it becomes economically not viable. So it becomes impossible. At HydroQuebec, what we do instead, we rely on past data. We gather all the outages that happened for the last 5 years, and we process all the outages, vegetation outages, and we identify the worst line in order to do what we call a vegetation control. However, this technique is reactive. So when you react, it's a little bit late. However, we believe that maybe there's a way to see things coming, to be proactive. So last year, we scanned with the vehicle LiDAR 150 kilometers, and we had what you see in the right side of my slide. We had point clouds. Like for each point that you see, we have at least 3 information: the X, Y, and Z coordinates, and sometimes also you have color. So, and with this point cloud, it's easy for human to spot if there's vegetation close to your distribution network. So our idea is, if human can do that, maybe an algorithm can also do the same thing. An algorithm can automatically detect the hotspots where vegetation is close to power lines. This is our main idea. We can easily see in this picture of pine cloud how close is the tree to our overhead power lines. So we can see it's far from the power lines by 2.4 meters. So human can do that really easily. And our idea is, why not do the same thing with an algorithm to be able to automatically detect the location of lines and also detect how close the vegetation is to our overhead power lines. And what is novel? The novelty of our algorithm is we start by detecting poles. We believe that detecting poles, first of all, it's an easy task because poles have, as I said before, they have specific shape, cylindrical, specific height, color, radius, and so on. So we start by detecting poles, and after that we connect closed poles together, and we believe that between those poles there should be a power line. So this is the main idea of our algorithm. What is different from other works is we don't start detecting lines. It's not our first step. Our first step is to detect poles, and after that we believe that there's line between poles, there's power line between poles. So let's see how our algorithm works. This is the big picture of our algorithm that we are proposing. So if you want to know all the details and if you want to reproduce our algorithm, I invite you to read our paper. You're going to find all the parameters that we have used in order to do the poles and line detection. But let me describe the big picture. First of all, we have as an input the LiDAR, the point cloud as an input. For example, for the last example of point cloud that has represent a distance of 500 meters of recording, it weighs more than 300 megabytes. It's a huge amount of data that you have to process. So we take that point cloud, we use the PCL library, which is free. We use it in order to remove the ground. And by doing that, we reduce the amount of data by 60%. After what, we clusterize, we extract clusters, so individuals from our point cloud, and we analyze each cluster or each individual in order to find our power pole. Once we do that and we have our poles, so we connect the pole together and we extract the plane between two poles, two consecutive poles. We can do that by processing the distance between each pole. And after what, once we have the plan that is bounded by two poles, we try to find lines, and the lines represents the overhead power lines. Once we have the lines, we reconstruct our power line by a parabola, by a 3D parabola, and this parabola represent all the line between two poles. So once we have the parabola, then we can process if there's points, vegetation points that are close to our parabola. We can extract the number and the intensity of points near to our parabola, and that gives us a good idea about the vegetation and how close is the vegetation to our overhead power line. Let me show you with pictures how does work our algorithm. So let's suppose that we have this track to process, this point cloud to process. The length of this point cloud is close to 500 meters. As we can see, there's 7 poles, and also the weight of this point cloud is close to 300, is more than 300 megabytes. The first thing that we can do by using the PCL library, it's a C++ algorithm. It's a free algorithm, and you can use it in order to take off the ground. So we take off the ground by using a morphological filter, and as you can see, we've been able to reduce the amount of data by 60%, which is huge. And in addition, we don't need to process the ground, because what we are looking for are the lines and poles. So after what, we start clustering, we extract clusters, and each cluster represents individuals, and for each cluster, we can now try to detect the poles. Clustering techniques is based on the density of points and also the number of points and the distance between each point. So when you have the right numbers, you can extract really beautiful clusters. Now that we have cluster, now for each cluster we try to detect cylinders, always by using the PCL library. And we obtain these results. As you can see, our algorithm was able to detect poles, correct one. But however, as you also can see, there's two mistakes here. That's what we call false positive. The algorithm thought it's a pole, but in fact it's true trees. But for this one especially, it really looks like a pole. But it's not a problem for us because our algorithm, what he does is going to connect all the poles together that he has detected, and he is going to extract the plane between those two poles. So we're going to have an extra information, but still our main objective is to find the power lines. Now what we see is a mix of the pole that were detected, and you can see we have been able to detect 7 poles plus 2 extra false positive information. And after that, our algorithm, he was also able to extract between two poles, between two consecutive poles, he was able to extract the plane that is bounded by 2 poles, as we can see here. And also, as we can see here, a beautiful plane between 2 poles. And so, with this technique, we were able to reduce the original amount of data by 90%. And now, our algorithm will try to find sticks, or what we call lines, in this plane. And what is interesting, because we have a plane, so we can also ask our algorithm to detect lines that are only parallel to the plane. So it becomes really easy for our algorithm to detect good candidates as being part of a power line. And still, if our algorithm is also able to detect lines that are not parallel to our plane, it means maybe it's trees or vegetations or branches, and also it's an important information later to detect the intrusion by vegetation. Once we have detected lines in our plane, so what we have to do next is to merge all the lines in order to have a beautiful 3D parabola that goes from the top of the first pole and ends at the top of the next pole. So what you have to do is to find the right equations to model the 3D parabola in order to fill the gap and in order to merge all the lines that you have detected. So here it's a little bit tricky, but what you can do is you can split your problem of 3D parabola into 2 simple equations. So what you can do is, one, if you take your 3D parabola and you do a projection over the horizontal axis, you obtain a 2D line. And the equation of the 2D line is really simple: y equals ax plus b. And here it becomes really easy to find the corresponding value of a and b according to the line that you have detected in your plane. And now if you get back, you take back your 3D parabola and you do a projection over the vertical axis, you obtain what we call a 2D parabola. And the equation of the 2D parabola is ax squared plus bx plus c. And again, it's really easy to find the value of a, b, and c. Now, once you find the value of a, b, and c for the 2D parabola and a and b for the straight line, you have solved your problem, and now you have these beautiful 3D parabola that should represent your overhead power line. So let's talk about the limitation and the performance of our algorithm. First of all, according to our first experiments, we've been able to reach an accuracy of 94%, which is good. And however, the recall is 89%. And now for the power lines, the accuracy is 84% and the recall is 98%. So when we detect line, we are really sure it's a good one because, as I said, it's between two poles. And also the distance between our model parabola, our 3D parabola, and the real overhead power line is an average of 20 centimeters, which is this far. However, after a lot of experiments, we discover some strong limitations. And even if the accuracy is 94%, but we did discover that for some other tracks, for some other point clouds, the accuracy will be way lower than 94%, and it can reach, let's say, 80%. And the problem is when you miss one pole, so you will miss two lines because there's always two lines connected to the power pole. So first of all, we did discover that the speed of the mobile LiDAR can impact the accuracy of our algorithm because the density of the points changes, and the PCL algorithm is based on uses the density as an input in order to detect cylinders. Also, depending on the LiDAR configuration, you could have more points or less points. So again, it will impact the poles detection. And also we did discover, for example, in this case, when there's occluded poles, you can see the red squares. So not our PCL algorithm or our algorithm that uses PCL is not able to understand that these three parts of the poles are from the same one. And maybe if you merge all the three parts, you're going to have all your pole. But our algorithm will consider that this is not a pole because it doesn't have the height of at least 6.5 meters, and it's a kind of problem. And also sometime your LiDAR, mobile LiDAR, is on a road that is higher than the field, or maybe the opposite is lower than the field, and your pole, for example, is located on a hill. So with your LiDAR, you can only just detect a small portion or half of your pole, so it becomes impossible to detect that pole as being a pole. So you've probably heard about deep learning algorithms that are really strong at detecting objects in 2D images. So for us, we started using deep learning architecture in order to detect poles in 2D images. And you can see the result in the right side. So our deep learning algorithm can detect poles in 2D images. But what you don't know is your LiDAR vehicle is able at the same time to record point clouds, but also images according to several cameras. Those motorized LiDAR, they have 6 cameras, and each camera has a direction, orientation, and so on. And if you are able, with 2 different cameras, with 2 different directions, to detect the same pole, so you have an intersection in a space area of that pole. So a frustum, you can extract a frustum from a 3D object according to your 2D cameras. Let me repeat it again. In other words, if you have a camera that has this direction and they detect on 2D world or 2D pictures a pole, and you have another camera that detects, for example, for another direction, the same pole in the 2D world, like in 2D pictures. So the intersection of 2D cone or 2D lines gives you what we call a frustum. It's a cube in a 3D environment. And now, because you have detected something, you have detected your pole, so you expect that in that cube, there's a pole. In that 3D area, in that frustum, you have a pole. And that's what we did. So we've been able to extract frustum, it means a cube in a 3D environment, with the help of our 2D deep learning algorithm. And today we are able to detect 95% of the poles in 2D images. To extract frustum, you can see the frustum are like a cube. And because we were detecting poles, so we extract frustum where in a frustum of point clouds where it should be a pole there. Now, so the frustum extraction today is automatic. And also we are using the PCL algorithm just on that small area, just on that small frustum, small point cloud in order to identify our pole. And because we are pretty sure that there's a pole there, so what we can do is we relax some constraint. We use a really simple cylinder detection in order to find the pole, and with a high certainty. Let's move to the conclusion and future work. As a conclusion, our approach is different from other LiDAR technique because we start detecting poles and then we extract plane in order to find the power lines. Actually, we have an accuracy of 94%. with a recall of 89%. We strongly believe that combining the 2D image segmentation and frustum extraction will improve the performance of our algorithm. It's a work on progress, and still our main objective is to automatically estimate and locate the hotspot of vegetation intrusion. Now we are able to adequately detect the power lines. The next step is also to automatically evaluate the hotspot. And finally, we start testing deep learning algorithm and to analyze point clouds. And those architecture like PointNet++ or PointCNN are able to process point clouds in order to detect objects like PCL. So thank you for your attention.